Hang on now. So what we can do is we use the graph to study some properties like we did last time. The session I have exactly last time. So let's see. Okay, so maybe we can all, recreate this graph that we had from last time. And if you remember all the way back here. Okay, so this was so let's recreate the same graph we had last time. So we basically do this. G is equal to the graph with the edges. And the edges are 1, 2, 1, 4, 1, 6. 2, 3, 2, 4. 3, 4, 3, 7, and then 4, 5, 5, 6, 5, 7, and 6, 7. And then we make the directed equal to false. Does everyone have that? You had from last time, right? Okay, good. So, alright, so now we have that, and then A was the as adjacency of G. So we have now the, so I want to make it a sparse equal to false. So now we have the adjacency matrix which we had last time also. So what we can do is, let's, so there is this function actually in iGraph called the graph-led basis. So I'm going to use that to basically help me figure out what the terms of the graphlets. So let's look at the graphlets. So the graph-led basis should give us, as this says, exactly the right thing. Okay, so return a list of subgraphs with the corresponding weights. The second and third function correspond to the this for the graph-led basis. Okay, so it returns the cliques. Okay, and the weight of the subgraph. Alright, so let's just run it and see what happens. So we run it and we say too computationally intensive. Yeah, me too. This is the workspace. Oh, just copy it. Oh, I should have saved it as a... So I'll try one more time, I don't know if it works. Graph, otherwise I'll do something else. Okay, we'll do something else. Did it work for anyone? Did anyone try? Okay, so in that case, I'm going to do something else. So let's do the, we can start with the modularity. So what I want to do is I want to compute the modularity of the input graph. So let's get back to this one. So we create this graph. And so now we need to know the cluster indicator vector. So in this case there were 7 vertices, right? And this was the graph we are studying, right? And we are going to break it up into 2 parts. So 1, 2, 3, 4, and 5, 6, and 7. And then we'll compute the modularity score that we have. What is it? Yeah, this one. So let's see if you can compute this. So let's just say cluster 1 is C1, 2, 3, 4, 0, 0, 0. Right? So there's a cluster indicator vector for cluster number 1. And cluster number 2 is C1, 1, 1, 0, 0, 0, 0, 1, 1. Okay, so now we have our cluster indicator vectors. So the first thing we want to do is we want to verify some of these things that we say are equivalent. So if you want to know the total internal flow, like how many edges are internal to cluster 1, right? So that would be, let's say, the EC1. Okay, so the number of edges that are internal to C1, it should be what? It should be C1 times A times C1, right? So first I define A as adjacency. G sparse equal to false. And then I say, okay, here's the A matrix. So it's easy to verify in this case, but if I want to know the number of internal edges, so I'm just going to call it EC1. So how many edges are inside cluster 1? So that should be transpose of C1 multiplied by A multiplied by C1. Right? So C1 transpose times A times C1. This should tell me how many edges are internal to that cluster. So EC1 now is 10. And it's actually double of what it should be. Yeah, it's 2 times the number of edges actually. Because it's counting twice in this process. So the actual number of edges is half of that. So the actual number of edges is half of that, which is 5, which we can verify here. Right? So the number of edges is 1, 2, 1, 4, 2, 3, 2, 4, and 3, 4. So there are 5 actual edges. And when you do this multiplication, it counts every vertex, basically every endpoint twice. So that's why the total. And likewise, EC2 is simply, I can copy that. So this is C2 and C2. So actually it should be half of that. So it should be EC2 by 2. That will be the total number of internal edges in cluster number 2, which we have from here as well. So if you look at 5, 6, and 7, you have 5 to 6, 5 to 7, 6 to 7. And so this submatrix here, from this point onward, these 3 values on the right hand side, the lower right corner, that tells you what is cluster number 2. So anyway, this is just a verification of what we already knew. The total weight is the sum of all the degrees. So that's fine. Now I want to do the modularity. So let's compute the modularity. The first thing we need to know for modularity is we have to do the internal weight, right? Weight from CI to CI divided by weight, the whole weight, W to W. So we can simply add the total weight. So let's just define these things. So WC1C1 is actually the same as what we just did. So that's actually EC1, right? All the internal stuff. WC2C2 is EC2. So this is just the weight that is internal, the weight that is internal. From C1 to C1, C2 to C2. Actually, I should have put it capital internal. Oh yeah, EC1 is this thing I just computed, right? The total internal weight of that cluster. So I'm just actually trying to follow this terminology, right? So WC1 C1, WC2 C2, then we can do WVV, and then I can compute the rest. So the EC1, yeah, so we already computed that, So we have these two numbers. What about WVV? Well, this is simply the sum of all the weights. So we can actually just do sum of weight. I mean, in this case, the total weight of the whole matrix from any vertex to any other vertex, and it will be counted twice, which is okay. So we get WVV is this. So WVV should be 22. There are actually 11 edges, so it's double of that. So that means there are 5 internal edges, there are 3 internal edges, that's 8, and there are 3 cross edges, which we can look at this figure and see. If we go back, where is my no, actually I had it here. So you can see that in this cluster here, the first cluster, there are 5 edges. In the second cluster, there are 3 edges, and there are 3 cross edges. So the total 11 edges, and so the WVV should be twice of that, because every edge is being counted. It's being counted 2 times. Okay, so we got that term. Now what do we need? We need the CIV. That's the only thing that's missing. So we need to know how much edge is external, how much of the weight goes external to the cluster. So we say WC1 to V. So WC1 to V should be. So this is, remember, the sum of the degrees. Okay, so actually I can use the degree matrix for this. So let me first define the degree matrix. So the degree matrix is the diagonal of degree. So we just take the degree of G will give me the vector of all the degrees, and the diagonal of that will give me the diagonal matrix. And this matrix should be our standard 3, 3, 3, 4, 3, 3. Now, if I want to know the internal part, right? So sorry, I want to know the total weight leaving a cluster. So the total weight leaving a cluster, if you remember from last time, was actually T of C1, so the cluster 1, times the degree matrix times C1. So instead of the adjacency matrix, we use the degree matrix because the degree matrix has summed up all the weights, internal and external, right? So I want to know everything. So this is the complete weight that leaves a given cluster from C1 to itself or to anyone else. The total weight of that cluster, the volume of that cluster. So that should give me that. And I can repeat the same thing for cluster number 2. So for cluster number 2, it should be, So this indicator vector basically helps us do these operations using matrix notation, but otherwise you can do it obviously by simply adding things up. But this gives us a simpler expression to compute that number. So let's see now what we have. WC1 is 13, and WC2 is 9. So let's see if that adds up. So let's go back here and verify. So for cluster number 2 is 5, 6, 7, right? So there are, let's see, so C2 to itself is going to be 6, okay, double of internal nodes. All the internal things are counted twice, so which we already had from before, right? So the internal weight was 6. And the external weight, there are 3 external edges, so you say 6 plus 3 is 9. So that actually adds up to be the right number. Okay. Make sense? And likewise here, the internal weight was 10, okay, because every edge was twice. And then there are 3 external edges, so 10 plus 3 is 30. So we now have the total volume of each cluster. Okay, so now I want to compute so we have to do the subtraction, right? So the observed number minus the expected. So So the Q they trick is simply for each cluster now we have to do this. So it's going to be WC1C1 divided by WVV minus WC1V divided by WVV squared. So that's the first term in our modularity, right? So let's just verify that I did it right. So the internal WCI-CI or C1-C1 divided by WVV minus WCI-V divided by WVV squared. Okay, so I just repeat this one more time. And this we just replace this with C2. So that's it. So there are two clusters, and we just compute the deviation for each one of them and add them up. That's the total modularity score. So that's the process. So let's see what happens. So it turns out to be 0.21. Now, of course, to really see the effect of this, what we should have done is we should have created an alternative clustering, maybe a bad one, right, the worst one, and seen what the modularity score for that was. So now we are in trouble because I have to redo the whole thing. So I'm going to actually define a function called Q. So I'm going to say Q is a function of C1, C2. Okay, so this is just so that I can compute a few other clustering, and all we have to do is give the indicator vectors, and that way we can study what the modularity score is going to be for each one of those scenarios. So now I'll just copy whatever I did from before. So we just redo our steps, define these things. I can just excuse me. So WC1C1 is actually AC1 star A star C1. Then we do the WC2C2. Then you define the degree. Actually, degree was already defined from outside, so I can just use it. So yeah, just recopy these two, for example. Okay. Recopy this. Okay. And then WBB is sum of B if you want. Doesn't really matter. You can do sum of A, it's the same thing. And then I just compute the modularity and return. Any questions? Yeah. I'm assuming the graph is yeah. Otherwise, yeah. So right now it's just the same graph I want to study. Only the clustering will be different. So I'll give you different clustering. I want to compute what happens. So just let's return this. Okay, so that's our function. So the first C1, C2 is already there. So let's just see if it gives you the same answer. So I say Q, C1, C2. And I get my modularity out of that. So of course the idea was to contrast with something else. So let's define some really bad clustering. Okay? So I'm going to pick 5 and 6 and 2. Okay? I'm going to say 5, 6 and 2 belong to the same cluster. So C1, let's call it C1B, is a new cluster vector. I said 0, So 2 is in the same cluster, 3 is not, 4 is not, 5 is, 6 is, 7 is not. Okay? So 2, 5 and 6 belong to the same cluster. B would be the complement of this. So we can say 1 minus C1B. So now I don't have to retype that. Okay. We can just subtract from 1 and we'll get the answer. So let's just look at C1B, C2B. Okay, so we have the two. So obviously this is a bad cluster, right? We can look from the structure of the network that if you put 5 and 6 and 2 together, it's a bad cluster, and then you get something else. So ideally, the modularity should be lower, right? For a bad clustering, the modularity should be lower. So let's see what happens. So Q of C1B and C2B is actually negative. So yeah, it's really bad. Right? So it's in fact, they're saying that your clustering is even worse than expected, right? So even under random conditions, you would have seen, you would have expected to see a better clustering than what you got. Because negative means that you observed something, you expected something, and the observed is less than what you expect, which is like a very bad thing in terms of clustering. So yeah, so it sort of confirms that notion that modularity, I mean, it's a structural property, so it tends to do the right thing. But there are some cases, pathological cases, where it can have some issue. Maybe try one more. Let's try
1, 2, 4 in 1.
Yeah, 1, 2. Yeah, this one. This cycle here. 1, 4, 5, and 6, and then the rest of the 3. So I'm going to make C1C is C of, I said what? 1, 4, 5, and 6. Okay. So 1 is 1, 2 is 0, 3 is 0, 4, 5, 6, 7. And C2C would be 1 minus C1. Oh, redo. C2C is 1 minus C1C. And the modularity for C2C, sorry, C1C and C2C. Right, so it's actually worse than what we have. And the worst part is coming from this dangling, the 2, 3, and 7, right? They're not really good. I mean, when you cut the graph, it will be just a chain. It will be a linear chain. And the other side is not bad. I mean, there are 4 vertices that are connected to each other in a cycle. But that's definitely worse than our initial cut, right? So we cut right here. We get a triangle and a nice dense. So you see the density is actually preserved. So the modularity is sort of saying that you have many more internal connections than you have external connections. And so it sort of confirms those that trend that we have. So generally modularity is a good, it's not the best always, but it's a decent and a good scoring scheme. That if you have a clustering, it will tend to do the right thing. So that's the demonstration of modularity. Now one thing to try out would be this. Last time we did the ratio cuts. I want to do a modularity cut. So the modularity cut. So just to study what are the properties of the modularity matrix. Excuse me. So this is the modularity matrix. So I'm going to define this. So it's basically the matrix is defined. It's extracted from the same thing that we had before. Now I'm using this other term here called the trace of the diagonal matrix. Okay, the trace of a matrix is simply the sum of the diagonals. Okay, so TR of the delta is the sum of the diagonals. Okay, which is actually what I also used here. If you saw my function, the sum of the was actually the trace. Okay, the trace just takes the diagonal elements and adds them up. For any matrix, the trace of the matrix is the sum of the diagonal elements. In this case, it is a diagonal matrix, so only those elements really contribute. So this thing here is equivalent to the trace of the matrix. So the trace of the diagonal or of the degree matrix gives you the total volume, okay, the total size. So this is exactly that. So it's actually WVV. So this formula is nothing different from before. It's just written in a different way. So I want to use this to create my modularity matrix, which I think is the same thing. I think it is what it is, yeah. So we don't need to do anything else. 1 over trace. Okay, yeah, so then we're done actually. So we just compute the eigenvector of Q and then see what happens. So this, eigenvectors of the, not the, sorry, the GD transpose. Where is the modularity? So the difference is that I want the matrix, not the scalar. I mean, I can't compute eigenvector of the scalar thing. So this one is 1 sec. So I take the adjacency. I do the trace. That's divided by a scalar. So this one actually, I think let me just quickly check here. Because you have to go through a set of, so the idea was to create a matrix out of that. Okay, so here we are. So the matrix came out as a consequence of okay, sorry. Right, okay. So the reason you have a matrix in between is that I forgot. Okay, so this cluster indicator vector, what I'm doing is I'm pulling that out. So because if you multiply inside, you're going to get a scalar. Okay? So the idea is to keep the indicator vector separate and then see what is the matrix inside. So ultimately when you do the multiplication, it will be a scalar number. But what I want to do is compute an expression without the CI in it. So this is the modularity score, and right now the way it is written is going to be a scalar number, right? So this I got confused because this is when you do this, it's a quadratic product, and it will be a scalar value. Okay. So I want to pull the two CIs on the left and the right outside because they are going to be common terms on in this expression and in that expression. So the CI is common on both sides, so you want to pull that out. The way you pull it out from here, let me just say, when you take the dot product of two vectors, it's a scalar number, right? So this one is actually, I should open it in the other one. No. Let me just do this quickly so that you see the logic. Here. Okay, so if you look at this, di transpose ci, there's a square there, right? So it's like two scalar numbers which we are trying to take the square of. Now, if I can write it in this manner, I'm going to write this as, ci transpose di, di, and di transpose ci. It doesn't make any difference, right? So when you have, because this ci transpose di is a scalar, this di transpose ci is also a scalar. So the dot product is a commutative thing, so it doesn't really matter which order you do it. So it's actually equivalent to this. So you can just rewrite it in this manner. By writing it in this manner, the idea was to pull out the Ci terms. Okay? So inside you get di transpose Ci. And this is a matrix. Okay? So di transpose is a rank 1 matrix that we. So this is what appears here. Right? So when I pull the Ci out, you're left with d transpose. So that was sort of the idea behind doing this kind of step. Here it's easy to pull out. I mean, the Ci and the Ci transpose are easy to pull out. The only thing that is left is the A. So that's A minus D transpose. By the way, D is the degree matrix for the whole graph. So this is the matrix I really want to compute. So this is what I'm going to now show you. So we go from here. So what you want to compute is, you want to compute the, so let's go back to the original one. Okay, so C1 and C2, right? So here are my C1, C2, the 1, 2, 3, 4, 5, 6, 7. So first I'm going to compute the modularity matrix. So this is a new matrix. So I'm just going to call it MQ, modularity matrix. And this modularity matrix is A minus, actually first let's define the D. D is simply the degree of G. Okay, so you see D is a degree vector. So the matrix I want is, the MQ is basically A minus the degree times the degree, the transpose of the degree. Okay. Actually, first, before I do that, let's take a look at this. What is D times the transpose of D? This will be what we call a rank 1 matrix, because there's only one vector, and you're just multiplying by the transpose of that vector. So what happens is you get a matrix like this. So they're all linearly dependent. There's only one independent row, and there's only one independent column in this whole matrix. Others are all multiples of that. And that's why it's called the rank 1 matrix. The rank 1 matrices are very important because they actually give you the spectral decomposition. We haven't yet talked about that, but I'm going to show you because it's a very important concept. The spectral decomposition of a matrix. And this rank 1 thing actually plays a role in that. But for now, this is what the degree times degree transpose looks like. This is a matrix of the following kind. So now we want the MQ matrix, the modularity matrix, which I'm going to call MQ, because Q I define to be a function. This is a matrix back. So it's A minus D times TD. Okay. And we also need to divide by the trace. So we need to divide by the trace, which is the sum of the delta, sum of the degrees, whatever. Right? The trace is the sum of the degrees. So let's do that. So this has to be divided by the trace. Trace is nothing but the sum of the degree. And the whole thing also has to be divided by the trace. So the whole thing has, is 1 over, if you look at the formula, it's 1 over sum d times this, right? So that's my, just to flip back for a second, you have 1 over the sum of the degrees, then the whole thing in a bracket, A minus dd transpose over the sum, which is what I have. So 1 over the sum of the degree times A minus d transpose divided by the trace, by the sum. Okay, so this matrix now we have. So let's see how it looks. So that's what the matrix looks like. Now we are going to compute the eigenvectors and eigenvalues of this matrix, because we want to know the eigenspectrum of the modularity matrix, and we want to maximize the eigenspectrum. Okay, so your clustering should maximize, and this is again going to be very neat because hopefully, well, let's see. I'm not going to say anything until I find it. So I'm going to do eigen. So EQ are the eigenvalues, eigenvectors of the modularity matrix. MQs. Okay, so let's find out the eigenspectrum of this and then print out the values. So the values are so the problem, like I had said, one of the issues with the modularity matrix is that it can have negative eigenvalues. Right, so that, and we want to maximize the modularity, right? So if you want to maximize the modularity, you have to ignore all these negative eigenvalues. You cannot use them, which is okay in this case because this value is anyway 0. Okay, something to the power minus 17 is essentially a 0 number. So this is our demarcator. So in this case, what this says is that you really can only find 2 clusters. Okay, because if you go to the third one, you're already at 0, and then beyond that, it's all negative eigenvalues. So for this particular data set, we can only do really into 2 clusters using the modularity approach. So it's probably good to see what those might be. So let's look at the EQ dollar vector. Let's look at the first eigenvector. That's the first eigenvector. And this is enough actually to give us, the split into 2. Just one sec. Let me also look at number 2, what happens.
Sir,
Yeah.
The degree in maximization object modularity, sum is varies over the number of clusters. So the matrix of D is K cross K matrix, not N cross N.
It is n by n.
No.
N is the number of nodes in the graph.
Because the I varies over the number of clusters.
Okay,
Each DI is a column vector.
No, but you see, what I'm doing is, I am summing up, okay? So what I'm saying is that keep the, so I want to compute something in the internal, right? So, and the cluster indicator vector will tell me which cluster it is. So it will be actually a sum of k different terms. Okay, yes. So you have to do for cluster 1, for cluster 2, for cluster 3. But the matrix inside is
K columns.
No, the columns are not k. The columns are n. K is just the number of terms in the summation. K is the number of clusters. There are n points each, right? I mean, if you look at the, okay, just take a look at this, right? My C1 is what? It's a vector of size. It's not a vector of size 2, it's a vector of size 7, right?
And the DI.
And the D is also a vector of size 7. It's the degree of every node in my graph.
Yes, sir. Okay, I agree with you.
Okay.
But the DI in this summation, I think that this is different from this D. Because the D, I think it's a column vector, and it contains the degree of each vector in Ci.
No. Okay, so D is this, okay? To find the degree of a particular cluster, you have to multiply by the C times the degree times the C. Okay, the binary vector, when you multiply by the diagonal matrix, will give you the internal weights in the cluster. We can probably work it out. I mean, I can show you on paper because it's hard to sort of describe. But I mean, this is a good point though. I mean, so let's, if there's a confusion between the number of points and the number of clusters, the expression here is over all k clusters. Okay?
Yeah, that's why there is.
But the matrix of, so ignore that for a minute. The matrix A is an n by n matrix.
Yeah.
Yes.
Mm-hmm.
The degree vector is a n, is an n by 1 vector. Just look at this expression here, right? So degree vector is a n by 1, is an n by 1 vector. Degree vector over all clusters. Forget about the clusters. Okay?
And sum is varies over k. That's why there is only k columns.
I think okay. Forget about the cluster. We don't care. Okay? Don't worry about the cluster. This modularity matrix here is simply, just tell me the dimensionality of this matrix, right? The dimensionality of this matrix is n by n, right? Because A is n by n, right? And then the degree vector is an n by 1 vector, and the transpose will be 1 by n, so it will be n by n. So the Q matrix, so we are worried about the Q matrix, is an n by n matrix.
So D is n cross k, and D cross Q is k cross n. So when you multiply, you got n cross n.
I think, yeah, you are, You are right in one way, but there's a typo there. It's not di, it is d. Because it's a vector, right? So it should in this expression there should be no I there. It should just be d transpose c. Like actually, yeah, exactly. I think I copied it from there, but there is no. I mean the degree vector. Okay. If you restrict it to that cluster, yes, but you don't need to restrict it to that cluster because Ci will take care of restricting the degrees to that cluster, right? Because there are 1 and 0 entries. So when you do, right? So basically, let's come back here, right? If I want to know what is the degree inside C1, I don't have to say D1. I can just do C1, transpose times D. That will tell me the degree inside. So you're right, but there's a typo. I apologize. Yes, there's no DI. It's only D. Then everything works out fine. So this should be simply there's no DI. It's the degree vector. It's the degree vector. That's how you get the modularity. Does that clarify your question?
No, I am not.
Okay, so we'll talk about that. Okay. So we can do it after the lecture, that's fine. Alright, so we have that. What else do I want to illustrate? So we now know the modularity thing. Let's see, what else did we cover? We already did that. Oh yeah, sorry, the spectral decomposition. So let me talk about the spectral decomposition because that's actually a key, a key idea, right? And this is where the rank 1 approximation comes in. Oh yeah. So in this case, actually, 1 has all the information we need actually. So you can see eigenvector 1 has all negative values for 1, 2, 3, 4, and this one has the remaining 5, 6, and 7. Yeah. So basically, in this case, if you just project the data onto one-dimensional space, you will have your clusters. The negative and the positive are the two clusters. So we can just cluster the data using that information. So this would be your mapping. So it's just a one-dimensional mapping. We're saying that you take all the points and, all the negative points, 1, 2, 3, and 4, right, they'll be on one side of the number line, of 0. The rest will be on the other side. Those will be your two clusters. So modularity is giving us the same clusters as everything else. Right? So you can use modularity. So if you go back to the algorithm, so the algorithm basically says that you first project, and then the only difference is that you choose the maximum in this case as opposed to the minimum. So let's go back to the spectral clustering algorithm. The algorithm says that you go, here you go. So this was, remember, for ratio cut and normalized cut, and we solved the eigen problem. So we solved this problem, for a particular matrix B, which was the Laplacian or the symmetric Laplacian, and then we look for the smallest eigenvectors, and the smallest eigenvalues. But for modularity, you have to do the opposite. You have to look for the largest eigenvalue, largest eigenvector. So instead of, so B is basically equal to Q, this matrix MQ that I defined. And then you compute the eigenspectrum of Q. So then you pick lambda 1, which is greater than equal to lambda 2, greater than equal to. So pick lambda 1, lambda 2. In this case, you can pick the first two, but actually the first is also enough in this case. The reason we could not pick the smallest one for the Laplacian was the smallest one was always 0. So it did not really convey any information. Here the first one will also convey information. First one gives us pretty much the whole clustering we need. So we just have to do one-dimensional projection. All the points basically get mapped to this one line. So these points basically get mapped to a line, and you have the 0 here, and you can see that 1, 2, 3, and 4 have all negative values. 5, 6, and 7 have all positive values. Right? So from our R, we see that the minus 0.22, minus 0.5, minus 0.22, minus 0.32, they're all on one side, 1, 2, 3, and 4. So that's your projection. So minus 0.22, minus 0.5. So this would be, 1, is 0.22. This is 0.5 is 2. There's actually 0.32 is number 3 and this is number 4 or something like that. Right. 1, 2, 3 and 4, the other way around. So when you arrange them in a number, this is what the values look like. So all the points, basically 1 and 3, they are here, 2 is here, 4 is here. And they're all negative, and the rest of the points are all positive. So I can just do a clustering like that. Just one split is enough to get you the clusters. Okay, so that gives us the modularity based cluster. Okay, so now let's do the eigen decomposition, which is what we have here already. But I'm going to do it for the Laplacian. So let's compute the Laplacian matrix again. So Laplacian was D minus A. Okay, and we know that Laplacian is a good matrix, right? Laplacian is this positive semi-definite matrix. And this is a very key point because once you do the decomposition, so now I want to compute the eigen decomposition of the Laplacian. So E is eigen L. Now let's look at the eigenvalues first. E dot values. So these are the values. High to low, they're all non-negative. And E dot vectors is this whole set of vectors. Now one thing about the Laplacian is that it is a symmetric matrix and it is positive semi-definite. What that means is that every vector is going to be orthogonal to every other vector. So this actually defines a well-defined coordinate space. So we can verify that. So the way we check for orthogonality basically says that two vectors are at 90 degree angle to each other. Okay, that's what we mean by orthogonal. So in that case, the dot product should be 0. 90 degree cosine of the angle, cosine of 90 is 0. So we can just verify that. So you can say, U1 is, so I'm going to quickly write this out because this is important to see in this format. Number 1, U2 is eigenvector of 2, U3 is eigenvector of 3, U4 is eigenvector 4, U5 is eigenvector, and on purpose I'm doing this, in this way because I want to show you something. Because this is one of the key ideas in data mining and machine learning is that of approximation by lower rank approximation. And so this will let us do that low rank approximation right away. So I'm going to call L1 is basically E dot values. Actually, let us call it eigenvalue 1. E2 is eigenvalue 2. Oh, sorry. E3 is eigenvalue 3. E4 is eigenvalue 4. E5 is eigenvalue 5. E6 is eigenvalue 6. And E7 is eigenvalue 7. Okay, so here's the spectral decomposition. The spectral decomposition says that your matrix L, right? Your matrix L is actually, think of an onion. Okay, think of an onion. The matrix L is made up of layers, okay? One layer at a time. The first layer is U1, and the importance of that is given by E1. Okay? The largest eigenvalue gives you the importance of that layer. And the layer is as follows. It is actually, so I'm going to call it layer number 1 is U1, it's actually E1 times, and this is actually a product, but this one is a matrix multiplication, U1 transpose of U1. Okay? So what is this telling me? This is actually saying that if you take the eigenvector, the dominant eigenvector, okay, and you take the transpose, just like you took the degree vector and you did the degree transpose, you get an n by n matrix. Here also you get an n by n matrix. It's a rank 1 matrix. But what does this L1 look like? Okay, it's probably hard to see here, but this is the most important layer. Okay, so I'm basically saying that L is made up of a sum of multiple matrices. Okay, layer number 1, layer number 2, layer number 3, there will be 7 layers. The importance of each layer is actually given by the eigenvalue. How much of that matrix? So it's basically made up of 7 matrices, and the importance of each matrix is given by the eigenvalue. So this is known as the spectral decomposition theorem. It's like saying that so let me add a page here. So you take your matrix L, and I'm saying L is made up of 7 of these matrices. So L is made up of 7 matrices. Now each matrix, if you just add them up, you'll get something else. But the importance of this one is actually lambda 1. Okay. The importance of this is lambda 2. The importance of this is lambda 3. This is lambda 4, lambda 5, lambda 6, lambda 7. So the importance decreases, right? So the most important layer is kept first, and you keep on going down and down. And this matrix is a rank 1 matrix. It's actually U1, U1 transpose. Okay, it's just one rank, just that eigenvector times itself in a transpose. This is U2, U2 transpose, and so on. So we can just say this is actually, we say this is the spectral decomposition.
Here the time is the number of linearly independent rows.
Yeah. So that means it will correspond to the so the number of 0 values will tell you what the rank is. Okay. So if some eigenvalues are 0, that will automatically say that those layers are not important and the rank will automatically be lower. It's basically how many, right? Because each one of them is going to be independent of the other, and the 0 values will basically drop out. So anyway, this is the full spectral decomposition. It's basically lambda I, Ui, Ui transpose. So this is called the spectral decomposition theorem.
So there is some similarity between this and the SVD?
Absolutely. This is in fact pretty much just the, in this case, because it is symmetric and positive semi-definite, it is actually pretty much equivalent to SVD, because you can write this in matrix terms, and this is actually it's a very good question to ask, because this is exactly the SVD. So this expression, so let me write it down. So this L equal to the sum of lambda I, Ui transpose. I goes from 1 to n. You can actually write this in a matrix notation, okay? And in the matrix notation, you can write this as U, okay, lambda, U transpose. Where this lambda matrix is actually a diagonal matrix of the eigenvalues. So this is actually the vector U1, the vector U2, and the vector U7 in our case. This is going to be lambda 1, lambda 2, lambda 7, rest are all zeros. And this will again be, this will be U1 transpose, U2 transpose, U7 transpose. So this is U delta U transpose. And this is exactly SVD, or principal component analysis in this case, because it's a symmetric positive semi-definite matrix. It's the same as PCA, but essentially a singular value decomposition. So this is sort of the again the sort of the visual, or the, I don't know, just sort of the background understanding behind this is that first of all you understand that this is composed of these 7 layers, right? The importance of the layer tells you, so the most important layers will be up front, the rest will be later. And this is just a more compact matrix notation to write the same thing. And what this shows you is that there's a diagonal matrix in the middle, okay, that gives you the importance of each layer. And this is just U1, U1 transpose, U2, U2 transpose, So it's exactly the same formula as here if you work out the matrix part. But let's just verify this because this is crucial. And then the crucial idea in pretty much, I think one of the most important ideas is that what if you want to approximate L? Okay. So what happens sometimes is that you don't want to look at all the layers. Okay. You want to get what we call a lower rank approximation. So all you have to do is just throw them away. In fact, I can throw away everything except lambda 1. I get just a one layer, one rank approximation to my data. Maybe that's not enough, so I go to the first two layers. Okay? So that's a rank 2 approximation. That is two linearly independent, and these are also your two dimensions, right? So you're saying, I'm taking my big data set with a graph or some other data set and projecting it onto two-dimensional space. So this is like a one-dimensional approximation. This is like a two-dimensional approximation, a three-dimensional approximation. So you can stop wherever you want. So normally, you look at the values. You look at what fraction of the total eigenspectrum have I captured. And that's where you stop. You say, if I've captured 90%, I can stop, or 95% I can stop. And that can give me a good lower rank approximation to my data. So anyway, this, as I said, is a very, very fundamental idea behind a lot of the techniques. But let's just verify this in our context. So what I want to show is that L actually is equal to that, right? So let's just first make a new matrix called L2, which should be what E1. This whole thing, I'll just copy this over and over again. But maybe, yeah, let's just do this the hard way. So I'm just going to call this. Okay, I think this is fine. So let's do. Let me just copy this. So layer 1 is this. Layer 2 is this. Okay, so the second layer is just eigenvalue times the rank 2. Oh, sorry.
L2.
Yeah, too many changes to be made. Okay, so now third. Three, L3. Okay, then I can do 4, 4, 4, 4. 5, 5, 5, 5, and the 6, 6, 6, and finally the last one, 7, 7, 7, 7. Okay, so now I want to show that the matrix you now get by adding these 7 layers is the same. So I'm just going to call this matrix, let's just call this matrix, this is smaller. So small L is simply L1 plus L2 plus L3 plus L4 plus L5 plus L6 plus L7. Okay, so I have now a matrix. And the question is this small L the same as my Laplacian to begin with? The one that I computed the eigenspectrum for. So let's just do the following. L minus L, right? That will tell me if there's any issue with that. That will give me a matrix. Okay, now that looks like a bunch of numbers and it doesn't look very nice. But actually if you sum it up, it's an extremely small number, right? Now you say, why is it not exactly 0? It should have been exactly 0. The reason why it's not exactly 0 is because of numerical issues. So when you compute the eigenspectrum, you are doing numerical operations, and so it's but something to the power minus 14 is pretty much 0. Okay? I mean, so it's a very so if you want to make tolerance higher, you have to do infinite precision mathematics. The answer would be exactly 0. So this is exactly that. But now comes the interesting part. The interesting thing I wanted to show you was the low rank approximation part, right? So if you have L, I say I don't want to use the full rank, I want to use something smaller. So what if I just use the first 2 layers? Okay, what would I get? So let's call L2 basically L1 plus L2. So I just want to see, okay, is this a good representation, right? It's like a 2-dimensional approximation to my data. Is this a good representation for the full Laplacian? So what if I did the difference between L and L2? how much deviation there is, right? And the smaller it is, that means 2 dimensions is enough to approximate my data. So it actually turned out that it is actually a very good approximation to my data in this case. The first 2 layers, more or less capture everything I need to know. What about L1? Just L1 by itself. Am I doing the right thing? Yes. I'm sorry. One. Everything is looking nice, but there is an issue. Because the problem is when you just do that, you might be adding the positive and the negative terms. So actually I should be doing the square. I should be looking for deviation squared. Okay, and then taking the root of that. So technically I should not be doing this, I should be doing yes, I should be squaring it. Okay, so let's do that. So first is L, but not this, I want to do the square of that. Okay, so this way, if some entry is negative, some is positive, if I simply add them up, they'll cancel each other, possibly. Right? So I might get the wrong picture. But if I take the square, then I can't go wrong. Right? So all the deviations will be positive. So what I'm doing here is I'm saying, take a matrix L and take your approximation, whatever the approximation you have. Right? Take the square of that, because otherwise the positive and negative entries can cancel each other out. So that's the square of that. Okay, this will give me all positive numbers. And now I take the sum of this. That is the true deviation. So sum of these guys should be. Okay, now we are much better. So this is the actual deviation between my original Laplacian and my full approximation. Okay. And now I can do the same thing. So remember this L2 was simply L1 plus L2. So what is the deviation from L2? The squared deviation. Let's look at that. So the squared deviation of the original Laplacian with the 2-dimensional approximation is not so great anymore. So this was a huge difference actually. If I don't square, what was happening was that some negative term and the positive term were cancelling each other out and I was getting a very low value. So anyway, it was a good sanity check to look at that and see there's something wrong going on. So this is the deviation. So that means 2-dimensional approximation is not enough in this case. I should probably go higher. Okay? So what I should probably do is maybe add 3 layers. See what happens after 3 layers. And so the approximation should improve all the time. So the deviation should decrease. So the more layers you add, the deviation should get smaller and smaller. So in this case, if I do this now, the 3, and it goes down. So it's still not enough. I mean, it looks like, there's some, and of course, we do know the eigenvalues. So if you look at E1, you look at E2, you look at E3, you can immediately say that, right, you're not yet exhausted the, these are equally important, right? So, 5.6 is important, 4.6, 4.4 is still important. E4 is still going to be important. E5 is also going to be important. E6 is going to be important. So in this case, actually, you probably have to go pretty much to the end. That means the 6-dimensional approximation is probably only the last one you can ignore. Okay? Which we knew from the beginning anyway. That this was a rank n minus 1 matrix. So in this data set, there's not much scope for dimensionality reduction. Okay? So this is, so let me just do the last one. So let me just do L6 approximation. Well, L6 will be the same anyway. So L6 we don't worry about. L5. So up to L5 would be L1 plus L2 plus L3 plus L4 plus L5. And then we do this deviation from this one. So so it's gone down quite a lot. So now actually a 5-dimensional approximation is still reasonable. I mean, you can probably say that this is quite okay. So, but in general, this is very useful for very high dimensional data. Right? So if you have a data set with thousands of dimensions, then technically you can reduce them down to 10, 20, 30, 100 dimensions. That's a huge reduction from 1,000, all the way down to a smaller dimension. So that's the basis for the singular value decomposition. Alright, I guess we are done for today, so that's all I have.